Good morning, chemistry students. Here is the corrections for the homework assignment on page 195, questions 39 through 43. So question 39 asks you to calculate the percent composition of the compounds that are formed from these reactions. And letter A is 222.6 grams of nitrogen combines completely with 77.4 grams of oxygen. So this is one where you're going to use the equation that percent composition equals the grams of the element over the grams of the compound times 100, because they give you the masses. So to find the percent composition of nitrogen, it is 222.6 grams of nitrogen divided by the mass of the compound, which is the total of the two added together, times 100. So we have 222.6 grams divided by 300.0 grams times 100. Which gives you 74.2% nitrogen. Okay. Now we also want to figure out the percent of oxygen. So for the percent of oxygen, we're going to do percent oxygen. It's still the same equation, so it's going to be 77.4 grams of oxygen over the 300 grams of the compound times 100. Okay, so 77.4 divided by 300 times 100 is 25.8% oxygen. I would recommend that you calculate the second one rather than subtracting from 100, because if you subtract from 100 and this answer here is wrong, that automatically means this answer would be wrong as well. So there's A. Now we're going to do letter B. So same equation. So again, I still want to see that equation that our percent composition equals the grams of the element divided by the grams of the compound times 100. So we'll do our percent of sodium first, which is going to be 2.62 grams of sodium divided by 2.62 plus 4.04, which is 6.66 grams of compound. Okay. So again, to get the grams of the compound, I just took 2.62 grams of sodium and added the 4.04 grams of chlorine, okay, to get my grams of my compound, times 100. Okay, so this equals 2.62 divided by 6.66. And again, I have three significant figures here, so I want to use three significant figures, which is 39.3% sodium. So then to do my percent of chlorine, it is 4.04 grams of chlorine divided by the 6.66 grams of my compound times 100. Okay. So 4.04 divided by 6.66 times 100. And again, I want three significant figures, so that gives me 60.7% chlorine. Same thing, I suggest calculating this second one using the information given in the problem so that if you've made a mathematical mistake when you did the first one, you don't get the second answer wrong as well. So that's those two percent composition problems. Number 40 asks, the compound methylbutanoate smells like apples. Its percent composition is 58.8% carbon, 9.8% hydrogen, and 31.4% oxygen. Methylbutanate's molar mass is 102 grams per mole. What is its molecular formula? So this is asking us for the molecular formula. Remember that our molecular formula is some multiple of our empirical formula. To find that multiple, we're going to take the molecular formula mass and divide it by the empirical formula mass. So, given that information, what we notice that we're missing is we don't have our empirical formula. So this is really a two-part problem. The first thing we have to do is calculate our empirical formula, even though it doesn't say that anywhere in the problem. And to calculate our empirical formula, we're going to use this percent composition data that they've given us. So remember, there are kind of 4 steps to doing this. Step number 1 is we're going to assume we have 100 grams of our compound. And the reason we do that is because now our percentages become masses. So in that case, we have 58.8 grams of carbon. We have 9.8 grams of hydrogen, and we have 31.4 grams of oxygen. Now, one of the ways that we can interpret formulas, molecular formulas or empirical formulas, is that they're ratios of moles. So we need to use our molar mass conversion factor to convert these from grams to moles. And because grams are on the top in each of these, grams are going to be on the bottom. Now, remember, our numbers in molar mass come from our periodic table. And since this problem is using at least 3 significant figures, we want to make sure we use 3 significant figures. So remember, the easy number are the ones that go in front of moles. The numbers that go in front of grams come from our periodic table. So for carbon, that's going to be 12.0. For hydrogen, that's 1.01. And for oxygen, that is 16.0. So now I'm going to do that math, and I'm going to express those numbers with 3 significant figures. So that's 4.90 moles of carbon here. That is 9.70 moles of hydrogen. And 1.96 moles of oxygen. Now, remember, we've never seen a formula with C 4.9, H 9.7, O 1.96. So we can't have numbers like that. So our trick to get whole numbers like we need is to take all of these numbers and divide by whichever one is the smallest. In this case, that's the oxygen. So we're going to take all of these answers and divide them by the 1.96. So that gives us 2.50 moles of carbon. That gives us 4.95 moles of hydrogen and 1 mole of oxygen. So what that is saying right now is we still have empirical formulas with decimals in them, right? We're going to say this is about 5. But this is 2.5. So how do I get rid of that 2.5? Because I can't have 2.5. Well, that's 5 halves as an improper fraction. And to get rid of that 2, I'm going to multiply every coefficient by 2. So now I have 5 10, and 2. So that means that my empirical formula is C5H10O2. So now I have my empirical formula, so now I can use these equations, right, that I kind of wrote up here. So I need to figure out the molar mass of this. Remember, that's not something you have to show work for. Again, I'm going to use 3 significant figures. So carbon is 12.0, and there's 5 of them, plus 10 hydrogens at 1.01, plus 2 oxygens at 16.0, gives me a mass of, my empirical formula mass is 102.1 grams per mole. Now I need to find this multiple. So my molecular formula mass that they gave me in the problem was 102. Empirical formula mass I just calculated was 102.1 grams per mole, right? Which means my X is 1. What that means is my empirical formula and my molecular formula are the same. So my molecular formula is also C5H10O2. So that's the final answer to this question. So that's an example of how you do an empirical formula and a molecular formula. 41, calculate the percent composition of each compound, and 42 asks you to use those results to calculate the amount of hydrogen in the following amounts of these compounds. So we're going to do A right now. Percent composition, so this is where it's asking you to do the percent composition equals the grams of the element in 1 mole of the compound divided by the molar mass times 100. And again, the reason we're using a different equation this time is because they didn't give us the masses like they did in number 39. So we have to calculate molar mass. And this is one time when it can be helpful to show your work for molar mass. So in this compound I have calcium, I have carbon, I have hydrogen, and I have oxygen. I have 1 calcium. I have 2 times 2, which is 4 carbons. I have 3 times 2, which is 6 hydrogens. And I have 2 times 2, which is 4 oxygens. I'm going to go ahead and use 1 decimal place for all of these. So calcium's mass from the periodic table is 40.078, so we're going to call it 40.1. Carbon is 12.0. Hydrogen is, we'll use just 1 decimal place, so we'll call it 1.0. And oxygen is going to be 16.0. So we have 48, we have 6, I think that's 964, there we go. We're going to add all those up. And I get 158.1 grams per mole. So that's the molar mass of my compound. So to calculate the percent of calcium, it's going to be the 40.1 grams per mole divided by the 158.1 grams per mole times 100. For the percent of carbon, it's going to be the 48 grams per mole divided by the 158.1 times 100. For the percent of hydrogen, okay, it is the 6.0 grams per mole divided by the 158.1 grams per mole times 100. And then for the percent of oxygen, it's the 64 grams per mole divided by the 158.1 grams per mole times 100. So that's why it's kind of nice to leave your work for these, because those are the numbers that you need. So doing this math, and because I've used 3 significant figures kind of consistently, we'll just use 1 decimal place. This is one of those ones where significant figures is kind of weird. So this is going to be 25.4% calcium. This is going to be 30.4% carbon. This is 3.8% hydrogen. And this is 40.5% oxygen. So that is answering question 41. Now 42 says, using these results, calculate the amount of hydrogen in the following amounts of these compounds. So this is asking us to take this answer here and use it as a conversion factor. So remember, if we assume we have 100 grams of our compound, then that means we have 3.8 grams of hydrogen. So this is the conversion factor we're going to use. So in this problem, they give me 124 grams of my compound. Grams of compound have to go on the bottom. Grams of hydrogen are going to go on the top because they want to know how much hydrogen. And we know that in 100 grams of compound, we have 3.8 grams of hydrogen. So we're going to take our answer and kind of do this math. So 124 times 3.8 divided by 100. And again, we'll do kind of 2 significant figures, so we get 4.7 grams of hydrogen. So now we're going to do the same thing for the hydrogen cyanide. So again, our equation is percent composition equals the grams of the element in 1 mole of the compound divided by the molar mass times 100. So again, helpful to show our molar mass. So hydrogen, carbon, and nitrogen. We have 1 of each. And so hydrogen is 1.0. Carbon's 12.0. And nitrogen is 14.0. I add those up, and I get 27 grams per mole. So the percent of hydrogen is 1 gram per mole divided by the 27 of the molar mass. For the percent of carbon, it's the 12 divided by the 27. And for the percent of nitrogen, it's the 14 divided by the 27. So 1 divided by 27. So again, we'll do 1 decimal, so we get 3.7% hydrogen. 44.4% carbon, and 51.9% nitrogen. So that's the answer to 41. Now doing 42, calculate the amount. Again, we're going to do the same thing with this. So this is, we're going to assume we have 100 grams of our compound, in which case we have 3.7 grams of hydrogen. So that's going to be the conversion factor we're going to use. So this time they gave us 3.78 grams of our hydrogen cyanide. Grams of hydrogen cyanide go on the bottom. Grams of hydrogen have to go on the top. We know that if we have 100 grams of our compound, we have 3.7 grams of hydrogen. And so we get, not 3.78, oops, this should be 378. There we go. So 378 times 3.7 divided by 100. And again, if I do one decimal place, I'm going to get 14.0 when I round grams of hydrogen. So again, that's how you do B of 41 and 42. Number 43. Which of the following molecular formulas are also an empirical formula? Remember, empirical means it's the lowest whole number ratio. So C5H10O5, which is ribose, sugar. Question is, can I make this an lower whole number ratio? And I can, right? Because this would be CH2O. O. Okay. So this would be the empirical formula for ribose, and this is the molecular formula. So this one is not also an empirical formula. Letter B, ethyl butyrate. So we have C6H12O2, and again the question is, can I reduce that? I can take a factor of 2, so it would be C3H6O. So this is the empirical formula, which means this is the molecular formula, and again the answer to the question is no, this is not also an empirical formula. For chlorophyll, C55H72MgN4O5. Again, because this magnesium there's only one of, that means that this is both an empirical formula and a molecular formula. So this is yes, it is. And DEET, which was used as a herbicide formula here. And again, oxygen and nitrogen there's only one of, so this is both an empirical formula and a molecular formula. So the answer to this one is also yes. So I hope that helped. I will tell you that you'll have some questions like these on a note quiz. So if you have still some questions, make sure you ask me. Have a great day. I'll talk to you tomorrow.